Video lecture on Public Economics, Chapter 6.3 on pay-as-you-go pension systems and the elastic labor supply. Hello and welcome back to our graduate course here on Social Security and Dynamic General Equilibrium. Today we study the Chapter 6.32 and 6.33 on elastic labor supply. So in Chapter 6.31, in the previous video, we looked at a lump sum pension. So we looked at the case that young households, workers contribute to the pension system in form of a lump sum pension, and this pension is passed on to this transfer is passed on to the retirees. And in the present video, we will look at the case when we introduce another distortion. This distortion stems from endogenous labor supply. So usually in modern economies, the contribution, the tax, is based upon wage income, upon earnings. So if we have to finance social security system all over this world, this means this introduces a distortion in the labor supply, as you got to know in Chapter 5 of our book on income taxation. So then we have two effects, the substitution effect and the income effect, because the net wage goes down. If we have higher social security contributions, we reduce our labor supply. Because of the income effect, we have lower income, we increase our labor supply. And we observe empirically that the substitution effect usually dominates, and we can estimate the effect by how much it reacts by, for example, the fresh labor supply elasticity, which we will come to in a moment. So when we introduce this realistic feature that pension systems have to finance themselves by putting a tax, a social security tax on labor income, how does it affect our results? That's going to be the question of this talk today. So let us get into the material. Therefore, I would like you to download the slides on Chapter 6 from my homepage. And let's get into the chapter on public pensions and elastic labor supply on slide 41. So far we have assumed that the contributions dt, so the contributions d in period t, are lump sum. Now we assume that they are a tax on wage income tau WT LT. So our wage income is WT LT, W is the wage rate and L is our labor supply. We have learned in the beginning how large are these values for tau. So in 1995, for example, the contribution rate was already 24% in France, 23% in Germany, and 42% in Italy. So these rates are even projected to increase over the upcoming years. And we will often use a contribution rate of tau equal to 30%, which is in the range of values observed for Southern European countries like Italy. In the United States, it's a little bit lower, or substantially lower right now. So this changes, of course, our budget constraints. So 24 is our budget constraint at young age. We have net income 1 minus tau WT LT. So we only have labor income, we only have earnings. This is the only sort of income we have. We do not have capital income because we are born with zero capital. And we can either consume it or save it, C1T or ST. There's no super index with savings because there's only one cohort that's savings, the young cohort, which is indexed with the number 1. So we do not need to index savings. The old cohort will not save, they will consume all and die. Equation 25 is next period consumption, C2T plus 1 at old age, and we consume our savings Of course, we earn interest rate RT plus 1 on savings, and we consume the contribution of the next generation DT plus 1. So the next generation contributes DT plus 1 dependent on its labor supply. And because the next generation is larger in size, we have to multiply the individual contribution DT plus 1 by the number of children each generation will have, and that's 1 plus n, 1 plus the population growth rate. So this is, as we have talked about, n, the population growth rate also determines the return of the public pension system, the rate of return. We can now solve equation 25 for the savings and substitute it into equation 24 to derive the intertemporal budget constraint, which is given by equation 26. So when we maximize intertemporal utility subject to this budget constraint, let me remind you of the intertemporal utility that we are using. Sorry for this. It's presented in equation 16. So we have log utility in consumption C1 and C2. Old age utility is discounted with the factor beta, and we have disutility of labor in the specific form here in equation 16. So disutility from labor is nu 0 times L to the power 1 plus 1 over nu 1 over 1 plus 1 over nu 1. So this is a typical utility function for utility or disutility from labor. It has some neat properties, so we will observe that nu 1 can be identified as a so-called Frisch labor supply elasticity. And it's a good utility function in order to model the distribution of labor supply. So when we have heterogeneous agent models with many different households, many workers, and workers with different wealths, well, then we have, of course, the richer agents work less usually. And with this kind of function, we are able to model the distribution of labor supply in economy very well. It has one drawback, so this function is not comparable, not in accordance with long-term growth. So if you have long-term growth, here labor supply usually would decline to 0 in the long run, and we do not observe that people do not work at all. We observe a secular decline in labor supply, but it's very slow decline, so usually we do not apply this function 16 in models with growth. So when we maximize this function subject to the intertemporal budget constraint 26, we derive the 3 first-order conditions 27 with respect to the derivative, setting the derivative of the Lagrangian of C1, C2, and LT equal to 0. So 27a and 27b, you know them from the last video. These are the first-order conditions with respect to consumption at young age and old age, and we can, of course, combine these two equations to get our first-order Euler equation here. C2 t plus 1 is equal to beta times C1 t times 1 plus r. This is our, of course, Euler equation that we know from this chapter already. The third equation is new. That's the first order condition with respect to labor supply. So on the left-hand side, we have the disutility, the marginal disutility from working an extra hour. And in equilibrium, this must be equal to the increase of utility that we get from working an extra hour. When we work an extra hour, we get the net wage 1 minus tau times WT. And these goods, this net wage will provide us with marginal utility lambda t 1 over C1. And of course, we should be indifferent between these two uses of the marginal good or the marginal hour that we are working. It should provide us with equal extra utility, marginal utility, if we use it as leisure or if we use it as labor to earn the net wage 1 minus tau times WT. Notice that when we take the logarithm of 27c, we get to the first equation on slide 44. And when we take the total differential, we get to the second equation. Notice, of course, that the derivative of ln LT is 1 over LT. dLT is the differential of LT. It's a small, very small, infinitesimal small increase of labor supply. And we also have a component d lambda t over lambda t and the differential of the net wage 1 minus tau WT over 1 minus tau WT. The parameters nu0 and nu1 are constants, so there are not there's not a differential on these variables, on these parameters, because they stay constant. Now, when we keep lambda t, the marginal utility of income, constant, then this equation, the second equation, the total differential, implies that nu1 is equal to the expression on the left-hand side of this equation. And we have used partial operators here, partial LT over partial net wage, so the partial derivative of labor supply with respect to net wage, because we set lambda constant. And we call this expression, nu1, the Frisch labor supply elasticity. It tells you by how many percentages labor supply increases if the net wage increases by 1% for constant marginal utility of income. And we have already met this Frisch labor supply elasticity in chapter 5. There I've provided you with empirical estimates of this value. It's between 0.3 and 1. And we will use a lower bound here in the following 0.3, and you're encouraged to do sensitivity analysis of our programs when this Frisch labor supply elasticity is increased to 1. And I will point out how this will affect our results. So now we can substitute our Euler equation, our intertemporal first order equation, how much to consume today and how much to consume tomorrow, so how much we should save, and so that we have higher consumption next period, and how much we should consume today. We can substitute this in the budget constraint in equation 26 and derive the second equation on slide 45. Next, we substitute C1t in our first order condition on labor supply. So we substitute C1t in equation 27c, and notice that lambda t is 1 over C1t, to derive equation 28. So this basically is our first order condition on labor supply, after we have substituted the budget constraint and the Euler equation successively in equation 27c. Now let's get to the second equilibrium condition that we need. So the first one will be this new condition that we have our labor supply is determined endogenous. That's new to the model that we considered in section 6.31. Now we look at the second equation, which is our capital market equilibrium condition. We know that savings are equal to net wage minus consumption. We again substitute consumption C1t, which from the previous slide, in this expression, and derive savings. Now in capital market equilibrium, we have the condition that the savings, the aggregate savings of the workers at the end of period T are the beginning of period t plus 1 capital stock. So 1 plus n times kt plus 1 is equal to st. When we substitute savings from 29 in this capital market equilibrium condition, we derive equation 30, which is our second equation. Now we only need to calibrate two new values, which are nu1 and nu0. We have one extra condition to do this, which is our labor supply, first order conditional labor supply. So we use this extra condition on labor supply to calibrate nu0. And we use empirical evidence to determine the fresh labor supply elasticity to calibrate it nu1 equal to 0.3. And in order to calibrate nu0, we also use the condition that labor supply is equal to 0.3 in steady state without public pensions. And then we can calibrate nu0 from this equation here in steady state and derive it's equal to 257.15. So what we got, we have two equations, equation 30 and equations 28. We look at the steady state, so that labor supply L is constant and capital stock K is constant. Then we can compute W and R, the two factor prices, with the help of the first order conditions of the firm, so that the wage is equal to the marginal product of capital, interest rate is equal to the marginal product of capital. We have the parameter tau, which is our social security contribution rate equal to 30%. We can determine D from the equilibrium condition of the social security authority, so that the contribution is equal to tau times WL, which is equal to 1 plus n times the pension. So we have two equations, 28 and 30, in the two variables L and K. And we have the unknown, these two unknowns, and solve for them. Now when we want to calibrate, we substitute our two unknowns L and K by K and nu0, because we have L is equal to 0.3. Solve this nonlinear equation system 28 and 30 for nu0. This provides us with the value 257.15. And when we consider a change in our pension policy, we keep nu0 constant, because this is a deep parameter, a structural parameter in our model, and we compute endogenously our labor supply. So, and this is done in the MATLAB or Gauss computer program, Chapter 6, Social Security 2.m. And when we apply a change from tau equal to 0, from the case of no pensions, and compare it to the case with pensions, 30% contribution rate, like in Southern European countries, we notice that we have a decrease in the capital stock output and welfare. It's more pronounced than in the case of an elastic labor supply. Why? Because we have an additional tax wedge in our model. We have a distortion of the labor supply decision. We only get 70% of our gross wage, and therefore our labor supply decreases, it falls by 2%. The magnitude of this fall, these 2% here, of course, is determined by our fresh labor supply nu1. So you can see this from equation 28. If nu1 increases as our fresh labor supply elasticity increases, so our response to an increase in wage, or in this case a decrease in net wages, then our labor supply responds larger. And here in this case it does not even fall by 2%, but if we go up to, let's say, 1, fresh labor supply elasticity of 1, it even falls by 4 to 5%. You are welcome to check this in the computer program. Of course, if you use a different mu value of mu1, like let's say mu1 equal to 1.0, you also have to recalibrate nu0 so that you have in initial steady state also have a labor supply of equal to 0.3. We find that steady state output falls by 30% if we introduce a pension system, and the welfare costs are an unbelievable 39% of consumption. So 39% of consumption, just to get an idea about the magnitude. If you have something like an average consumption expenditures in the United States of something like $20,000, this might even be a lower bound to it, and then this amounts to $8,000. So the pension system, according to our little model, and I've already pointed out that is how it changes when we look at a large-scale OLG model, is almost 40% of total consumption, which means that the average Joe, the average guy in the United States, sacrifices consumption at the amount of $8,000 in every period, in every year of his life because of the pension system. Well, that's a tough number here, so why don't we abolish pensions? And we will talk about this in the upcoming lectures. But let me already emphasize this huge welfare effects of pensions. When we look at a large-scale OLG model with annual periods, this number is much lower, so it reduces, but still amounts to a couple of $1,000 each year for each American as the welfare cost of pensions. And we have to wonder and ask the question, so why do we have the pension system at all? Now let's go one step further. Pension system in this world are different with respect to the indexation of the pensions. What does it mean? In some countries, like particularly the English-speaking countries, we observe that the pension is not closely related to the contributions. A little bit, but not much. In other countries, especially in Southern Europe, this relation is almost one-to-one. So if you double your contributions to the pension system, you also will receive a pension twice as big. We can characterize these different pension schedules in this world by equation 31. So your pension in old age in period t plus 1 depends on your contribution in period t, and your contribution is denominated by the variable x here. And your contribution is tau times wt times lt. Now we have a pension schedule that also has a lump sum component, pension mean. So if your pension system is a pure flat rate pension system with rho pen equal to 0, your pensions are completely rho pen equal to 0, completely independent of your earnings history. You receive a lump sum pension. This is the case we have considered so far. So we do not account for the fact that if I contribute more today, I will get a higher pension tomorrow. In the following, we will study that we have an indexation of your pension with regard to your previous contribution. So the lower pension mean, the lump sum component, the higher rho pen, the more related is your pension to the contribution. We talk about a regressive pension system if rho pen is high and pension mean is low, and we talk about a progressive pension system if pension mean is large and rho pen is small. So there are two progressivity measures to measure how much the pension system redistributes. And here redistribution means that people who contribute much provide much of their contributions to other people so that the pensions are more equal. One is the Gini coefficient of pensions, and the other one is the pension progressivity index, which is 100 minus the ratio of the two Gini coefficients, pensions income divided by earnings Gini. If the Gini of the pensions income and the Gini coefficient of the earnings are equal, then there's no redistribution. And of course, then this pension progressivity index is equal to 0. If it's equal to 100, we have a lump sum pension. And then the Gini coefficient of pensions, of course, is equal to 0. And then we talk about a progressive pension. Now let's take a look at some empirical values here. So Canada, the Gini of pensions is 3.7, which is extremely low, so basically lump sum pension, and therefore we have a progressivity index close to 100, it's 87. In the UK, it's also above 80. In the US, it's an intermediate case, it's 41, the progressivity index, and in Germany, it's close to 27. So if we somehow take a look at the Anglophone countries on the one hand and the Southern European countries, also including perhaps Germany, we observe that in the Anglophone countries, their pension systems are very progressive. So the average index of the Anglophone countries is 82 according to the OECD in 2030. And in Southern Europe, on the other hand, it's 23. So in Southern Europe and in Germany, pensions are related closely to your contributions, one-to-one. And if you have not contributed because you were sick, you did not work, well, that's too bad for you. You will not get income from the pension system in old age. Just the other way around, in the UK, in Canada, in the Anglophone countries, there the pension system redistributes much more among the retirees. And we wonder which system is better, the Anglophone countries or the Southern European countries. And we will discuss this in the end of this lecture. So Southern Europe countries, this would be the case that pension mean here in our schedule is close to 0. Anglophone countries, rho pen is close to 0. Now let's see how the budget constraint changes. So here in the budget constraint, we have our net wage and our discounted income from pension in period T plus 1 is equal to lifetime expenditures on consumption, so discounted consumption in old age and present consumption. Now let's form the Lagrangian. So we have the utility function, which is the same as in the previous subsection here. We have our budget constraint. In our budget constraint, we now substituted the pension schedule here. So our pension in old age is the lump sum component plus the part that stems from our contribution tau WT LT. So notice that when we increase labor supply, we get higher net wage income at young age, and we get higher pension income in old age. And of course, if people know the pension system and the rules and the schedules, they will consider the effect of the labor supply today on income today and income tomorrow. Oh, sorry, this should be a minus sign, not an equal sign. Sorry for this. And when we differentiate this Lagrangian with respect to consumption C1, C2, and labor supply, we get the equilibrium first order conditions 33A through C. So 33A and B are just the ordinary ones, the usual ones, which we already know, so we can solve for the Euler equation. 33C is new now, the additive term on the right-hand side here is new. This is the return that results from the increase in pensions in old age when we increase our labor supply. So what we do now, what's the optimal decision now? On the left-hand side, we have the disutility of labor. So if we work an extra hour, this is our disutility, our marginal disutility of labor. And in equilibrium, it should be equal to the increase in consumption, which follows from working an extra hour. When we work an extra hour, we get the net wage 1 minus tau times WT in this period, which provides us with marginal utility lambda t. And we get the extra income, pension income, rho pen tau times WT from working an extra hour in old age. The present value of this income is rho pen tau WT divided by 1 plus R, 1 plus the interest rate, the discounted value of this future income, the present value of our extra pension income, times the marginal utility of income lambda t. And this component is now an extra component, and it reduces the distortion of the social security tax on our labor supply, because now the disincentive to supply labor is reduced because of this extra income that we will get in old age. So we close the model by assuming that the social security budget is balanced, so NTXT is equal to NT minus 1 pension T. So remember that NT minus 1 is the number of retired people in period T, and this is equal to the number of young people in period T minus 1. So their aggregate pensions must be equal to the aggregate contributions, and the aggregate contribution is the number of workers, NT, times their individual contribution, XT. And then we are left, or we can characterize our equilibrium condition in steady state by the following 7 equations, 35a through 35g. So the first equation, 35a, is our Euler condition, our optimal first order condition. Since we look at the steady state, I dropped the time index t, this super index. And also I dropped the time index, of course, from the interest rate r. The equation 35b is the balanced budget of the Social Security Authority. Equation 35c and d are the conditions that the factor prices W and R are equal to the marginal product. Equation 35e is the first order condition on labor supply in steady state. Equation 35f is our intertemporal budget. And equation 35g is our well-known capital market equilibrium condition, so that the capital stock next period, which is the left-hand side, is equal to the savings at the end of period t, which is the right-hand side. And we can solve this model, this equilibrium conditions. So this is just a nonlinear equation system in 7 variables, and we can solve this model using numerical techniques. Let me first show you the results before we get into the code. So if we introduce a contributions-defined pension system with a contribution rate of tau equal to 30%, as we approximately observe in Southern European countries, in the United States it's less, and take rho pen equal to 0.5, this is just an intermediate case between the two cases of inelastic and elastic labor supply here. We will see in the results. The fall in labor supply is reduced by half, so from 2% to 1%. In comparison to the case we looked at before, so in the previous section we looked at the case rho pen equal to 0, so that contributions today of the individuals do not increase the pension entitlement in the next period. But welfare effects are still almost as high as they are the case if the pensions entitlements are not indexed to your contributions. So we can see that we can reduce the distortion in the labor supply, so that the labor supply is, the change of labor supply is halved, but the overall effect, the welfare effect, is basically driven by the huge reduction in savings, so that total consumption is still less by something like $8,000 in the United States, as we argued before. So let me show you in the MATLAB code. I've also provided you with the Gauss code how we have to implement this. So for this reason, for example, load chapter 6 Social Security 3.m into your MATLAB editor, or if you're using Gauss, chapter 6 Social Security 3.g. The programs are completely alike. You can basically compare them line by line and find that they're almost identical. So let's first run this computer code. So always run the computer code first to find out if it works. And you are asked to press a key here. So this is the solution with Social Security. So here you, for example, have the capital stock 0.0068. These are the 7 endogenous variables of your nonlinear equation system that characterizes the steady state. If we abolish pensions, we get the solution of 0.0182. So the capital stock more than doubles if we abolish pensions. And in the final part, we compute the consumption equivalent change, which is a welfare loss of 38% if we introduce pension. Remember, just steady state. We noticed in the previous video that, of course, the transition, there might be winners and losers. Now let's see how we implemented this in the computer code. Well, basically, it's all in the function here, steady state. This is our nonlinear equation that we solve. So here we have the 7 equations that we just looked at. Equation 1 is that the Social Security Authority budget is balanced. Equation 2 and 3 are the first order conditions of the firm, so that the wage is equal to the marginal product of capital and labor, and we specified the marginal product of capital and labor as a separate function wage. Similar for the interest rate R and a separate function interest rate where you provide capital and labor and the parameter vector nu, alpha, nu 0, nu 1, beta. Okay, and fourth equation is the first order condition with respect to labor. Fifth equation here is the Euler equation. Then we have the intertemporal budget of the household and the capital market equilibrium. The 8th equation in our model, which is our resource constraint, so that total production is equal to total consumption and total investment. Well, that's implied by these equations here. And this is what you know as Walras law. That's the law of Walras. So if you have, let's say, 6 markets in equilibrium, the 7th market is also in equilibrium. So we do not have the resource constraint here as an extra equation. So in the 7 endogenous variables here are K, L, W, R, C1, C2. Tau and rho pen are given. Rho pen, the progressivity index of our pension system, tau, the contribution rate, and then the endogenous variable here is pension min, the lump sum component. Okay, so let's get back to the slides. And let me point out a couple of economic results here. So we have wondered which one is the better system. Canada, United States, UK, or Germany and Italy. Well, there is a study by, for example, Fehr and Kindermann, who look at the optimal progressivity of pensions. And they find that the system in the Anglophone countries is preferable. Well, why is this welfare improving if you have a large redistribution in old age? Basically, what you forgo in the Anglophone countries, you have the extra incentive fact gets lost. So in Germany, you know, if I work an extra hour, my pensions will go up. So this induces me to work more in Germany. This effect is absent in these very progressive system like in the UK or in Canada. And this, of course, reduces welfare. On the other hand, what you do is you redistribute in old age. So you redistribute from people who with high income to people with little income. The people with high income, they have a small marginal utility of income because they're rich. So this will income rich. If you take this money away, take money away from these people and redistribute it to the poor people with a high marginal utility of consumption, of course, this increases welfare. And what you find in these studies is usually, yes, if you have heterogeneous agents and there's some rich people, pension-rich people in old age, it would be good to redistribute it to those with little pension. And the disincentive effect, because they have lower incentives to work hard, so that's a higher pension in old age, is not strong enough to counterbalance this effect. So we find, yes, from these studies, Anglophone countries have a higher welfare, provide a higher welfare to the citizen because they have such progressive pension system. Next, you compare these two countries. You notice that while the Anglophone countries are very progressive at old age, the continental European countries are usually progressive or mostly progressive while the people are workers. So we have high progressive income taxes when we are young. Of course, you may also ask which system is better, the one that's more progressive in old age, like the US or Canada or UK, or the one that is more progressive while you're still working and taking away lots of your incentives to supply work in young age. So in Germany, for example, we have one of the highest income taxes in this world, especially on labor income. So we have now surpassed Belgium this year, just a couple of weeks ago. This was in the news. We have little incentives to work because such a large part of our wage income is taken away. Our net wage, tax wage is around 60–70% for the median worker. If you compare the marginal product of labor, take away income taxes, social security contributions of the employees and the employers, and also consider that we have to pay consumption taxes 19%. Well, the tax wage is around 60–70% depending on your income. And if 60–70% is taken away from your from working an extra hour, your incentives are really low. So, for example, we have computed if my wife should go working, just a minor job, just a part-time job, and we have found that if she's earning 1,200 euros, which amounts to something like $1,300, $1,400, we are actually losing money, net income, because of our health expenditures. She drops out of my health insurance then. So this is a nightmare that's going on in continental Europe. People do not have an incentive to work because such a large component of the income is taken away from their gross income or the marginal product of labor. This is different in the United States and in the Anglophone countries. And public economists like me, we think that the Anglophone countries have a superior system. And one intuitive reason for this is, of course, the Europeans take away money from you taxes you high when you earn your money and try to build for your future. In the Anglophone countries, they redistribute in old age. Now, in old age, when you see, oh, I have little pensions because I got sick at 50 or at 55 or at 65, well, you cannot change it anymore. You're 70, you cannot go back into the labor market. At young age, when you're a worker, you can still change your fate and you become the master of your fate and your lifetime utility. And it's better to acknowledge, okay, now you're 60, 70, and you had bad luck in life, you only have accumulated little to the pension system. Well, at least do not starve in the streets here, let's give you a pension and redistribute at old age. But at young age, why take away the incentive to build up and do something in your life, achieve something, and build up capital and savings for old age? That's what we do in continental Europe, and it's sheer madness. So economists, even though there are a few little studies, think it's better to have the progressive system at old age during retirement, as shown here for the Anglophone countries, 82, the progressivity index for the pensions, but let people benefit from their work at young age and do not distort labor supply as much as we do in continental and southern Europe right now. Okay, that's the economic part of it. And now let me also discuss one numerical issue that we encounter here in this model with contributed pensions and endogenous labor supply. For this reason, let me switch to the whiteboard. So we can summarize our equilibrium in the two models that we considered today, the one with endogenous labor supply and no effect on the pension, and the one with endogenous labor supply and contribution-based pensions by the equation, for example, 28 and 30. And they provide the equilibrium conditions for the two systems. The one is where we just said rho pen equal to 0, the one where the labor supply and the extra contributions do not increase our pensions. So these are two endogenous equations in the variables kt, kt plus 1, lt, lt plus 1. So let me just show you again these two equations here. 28 and 30. 28 is the endogenous equation, the equilibrium condition with respect to labor and capital stock after we have substituted the marginal product Wt as a function of Kt and Lt, and the contribution of the next generation tau times Wt Lt plus 1. And equation 30 is our equilibrium condition in the capital market. And here again, we substitute Wt and Rt plus 1 by the marginal products, and notice that dt plus 1 is also related to Wt plus 1, Lt plus 1 in period t plus 1. So we can summarize these two equations here by a function f1 and f2 equal to 0. So two nonlinear equations in these endogenous variables. Now, how do we solve this? Let's say we have a given initial capital stock and we want to solve this problem over a time horizon. So let's assume we want to have time here and we have the capital stock here. We have given K0 and we want to, let's say, compute the transition to KT, to the final steady state. Well, this problem is far from trivial. because as you can see here, how can we compute the next period kt plus 1? So let's substitute k0 here. And we want to compute the next value k1, L1, but we do not know the variable L0 here. So we have three variables that we do not know, these three variables, but only two equations. So we cannot compute K1, L0, L1 starting in K0. How does this problem arise economically? The economic intuition is as follows. Well, if I am young at period 0, I know the capital stock of the economy, K0. I decide about my labor supply depending on my pension that I will get in the next period. But because my pension next period depends on the labor supply of the workers in the next period, the next generation. The decision of the generation in the next period, again, so let me at least show you my face here. In the next period, the workers in the next period also need to know the labor supply of the people in period T plus 2, because their pensions depend on this labor supply as well, on this decision, on the decision of the generation in period T plus 2 as well. And it goes on like this. And this recursive structure implies that we need to project the labor supply and the capital stock, which also determines, of course, the pension contributions, over the whole time horizon of this world. Okay, so how shall we tackle this problem? Can we solve for this problem? Well, for next 20, 30 periods, of course, we could write down all these 20, 30, 40 equations. It's much easier, however, to look at this problem starting in the last period. And let's assume that in the period uppercase T, let's say after 20 years, or 20 periods, after 20 periods, we are in the new steady state. So it's always good to solve this model if you knew where you're heading, where you're going to the new steady state. And what we can do then is we solve this system backwards. That's called reverse shooting. So let me show you this here again, the whiteboard. Let's assume we can solve for the steady state. You have seen the 7 equation that determines the steady state. We compute the steady state in period T. So sorry, this is time 0 and this is time T. And let's say we are in steady state after period T. So we can solve for the steady state. When we compute the steady state, this is just a nonlinear equations problems in 7 variables, as we've just noticed. It's not so easy to solve these nonlinear equation problems in many variables, and I will devote an extra video just on this topic, how we compute the steady state in a system of many nonlinear equations. So we will see an equation system of many 100 variables in about a couple of videos, about 2 or 3 videos ahead. Now what we will do now is we assume in period T we are in steady state and we provide a guess kt minus 1 of the capital stock in period T minus 1. And now let's look back at our 2 equations. In this case we have our 2 nonlinear equations. So we look at k uppercase T for our kt plus 1. We provide a guess for kt minus 1. We know the labor supply in the new steady state, which is LT. So, and then we may use our first order conditions, the function f2, to compute the labor supply LT minus 1, the labor supply in period t minus 1. Okay, so then we have all these four variables and we work back recursively. In this way, we ensure that the workers always know what the contributions of the old will be because they observe it. We work recursively, we work backwards. So then we just shift the index to t minus 1 and t minus 2. And we can solve these two equations here simultaneously for labor supply LT minus 2 and KT minus 2. And then we can work backwards in time until we hit period 0 and compare our capital stock that we get by this recursive dynamics to the initial steady state K0. Okay, and if it's not equal, for example, if our shooting method underestimates K0, we will increase our guess for KT plus 1. If it overshoots K0, so if it's above K0, we reduce KT minus 1. And this will be on top of this nonlinear equation problem that we solved with these two equations here. There's another nonlinear equation problem here to find an initial capital stock KT minus 1 that implies that our implied K0 is equal to the given one. So we have a nested nonlinear equations problem. The problem to find a starting value of KT minus 1 so that we get to the initial capital stock K0, that is the outer loop. And in the inner loop, we walk backwards recursively and solve a nonlinear equation system in the two equations F1 and F2. You have experience with such problems, recursive problems, just this nested nonlinear equation problems. And this is from the problem 3.5 in chapter 3 on overlapping generations. And in this problem, you proceed exactly as I just have described. And you can find this in my solution manuals, where I provide you an explanation of how we proceed in this nested nonlinear equation problem. You can download this computer code. It's problem P35, both in MATLAB and in Gauss. And you can find out how you solve such a nested nonlinear equation problems. And I would encourage you to compute the dynamics for this particular problem that we have looked at for the program Chapter 6 Social Security 3.m. I've also provided you with the solution to the dynamics of the problem where rho pen is equal to 0 in the program Chapter 6 Social Security 2.m.g, depending on whether you use MATLAB or Gauss. Okay, so let's summarize now. We have looked at the effects of elastic labor supply. The welfare effects is even more pronounced. Consumption, output, employment, everything falls even more. And we have noticed that it depends, the effect of labor supply depends on the indexation of pensions with regard to previous earnings, to previous contributions, to be more exact. We have argued that the Anglophone system is more efficient, providing higher welfare So far it redistributes, is more progressive in old age, while the continental is more progressive, taxes more progressively in young age as workers. And we have also noticed, of course, that the labor supply distortion depends on the fresh labor supply elasticity. I've used one of the lowest values that you find empirically. If you use other values that are used, for example, Trabant and Ulich use a value of 1 in their macroeconomic analysis, then of course the distortion goes up and labor supply will be reduced by 3, 4, or 5% in the case of pensions that taxes wage income or earnings. Okay, and I would like you to encourage you to play around with these computer codes, chapter 6, Social Security 1, 2, 3, and in particular look how sensitive they are with respect to the intertemporal elasticity of substitution. We'll find out if sigma goes up, so if you do not consider log utility, but let's say a risk aversion coefficient of 2, that the utility losses are even higher. You learned this in the last video. And you should also play around with the case, well, do we have depreciation rate? That's the topic of the problem 6.1, find also solution in the solution manuals. Or what is the effect on depreciation? What is the effect of a higher fresh labor supply elasticity? Now in the next video, we get to another central feature that is determining the profitability, the return on investment in public pensions. That's the rate of growth, because if I contribute today to pay the pensions of my parents, you contribute tomorrow to pay my pensions, well, tomorrow you will have, or let's say in 10, 20 years, you will have higher income due to economic growth, and therefore this will afford a higher pension for me. So the return on public pensions, of course, depends on both population growth and the economic growth rate. And one thing that I have not mentioned, the survival probabilities, which are upset now in our models, which we will get to in section 6.4, of course, is if the survival probability increases, if people live longer, this will reduce the return from the pension system, and that's what we observe right now. The return of the pension system falls because people live longer. Okay, so I've summarized the results from this exercise, and next we will turn to economic growth and public pensions.